So, without further ado, I'd like to welcome Caitlin Rowett, Tech Services Manager for Hillgrove Resources, to the stage. She's going to speak on putting a microscope on our Macro-stope. Please welcome Caitlin.
Hi, I'm Caitlin, and I'm here to talk to you today about our stoping and what we've been doing at the Cairman 2 copper mine for the last couple of years. Here are the usual disclaimers. And a bit of background on Cairman 2. So Cairman 2 is a copper gold deposit located in the southeast Adelaide Hills. It's about 60 kilometres from Adelaide, straight up the southeastern freeway. And it's a region that's had a significant history of copper mining in the area, with the original first discoveries of copper in the 1800s. Hillgrove commenced exploration in the region in the early 2000s, and in 2011 the open pit commenced. In 2023 the underground operations started, and we commenced stoping in late 2023. Since then, we've had continuous mine growth in both resources and reserves expansions. And so underpinning everything that we do on site is the geology of the Cairman 2 deposit. So a bit of background on our geology is that the Cairman 2 copper gold deposit is located in the southeastern side of the Adelaide Fold, in the Cairman 2 trough on the southeastern side of the Adelaide Fold Belt. Metamorphism in the mine corridor is unique to our deposit, and we see really coarse andalusites like that image up on the slides there. The andalusites can be up to 2.5 centimetres in length, and we can have beds that are really crowded in these andalusites, and that's really unique to our area and to the mine corridor specifically. Local mineralisation is hosted in the andalusite biotite schist, with local alteration marked by the presence of garnet, chlorite, staurolite and biotite, and then the subsequent deterioration of the andalusite crystals, where we start to see poikiloblastic textures. The age dating of the mineralisation is around 490 MA, and it's suggesting that it was hydrothermally introduced into the structural setting. Another interesting fact about our area, the alteration is really iron rich. So all of the minerals in the area become the iron rich end member, and that is a key part of our alteration sequence. We've seen that in spectral scanning from a couple of sources, including the high logger, and also in our infrared spectral scanning we use underground, done by Plot Logic. So looking into the alteration systems a little more deeply, the alteration domains can be split largely based on their presence of garnet or absence of andalusite. These alteration domains are really predictable, and we can identify them clearly across the deposit. So the mineralisation diagram up there, you can see where the mineralisation is largely hosted, and you can see the gradation of those other elements and minerals, And as you kind of move through the mineralogy and as it changes towards the mineralisation, it's really all variations on a theme. We see the same minerals but in different assembly as you move into the deposit, and we can use them as a vector of how close or how far away from the mineralisation we are. The main copper-bearing sulphide for the system is chalcopyrite, and we also see pyrrhotite in the mineralised zone, and it's the ratio of chalcopyrite to pyrrhotite that we see can also use as a vector to how proximal or distal we are to the main mineralising area. We see minor bismuthinite in areas of high bismuth, magnetite as well, and those are located in sort of specific small pockets within the deposit. The geometry and scale of the structurally controlled copper-gold mineralisation is highly variable, and it's the variability of this geometry and scale, it actually increases with the increase in copper grade. The reason for our variability in the mineralisation is that we're hosted in a shear complex. So the fluids have utilised that shear corridor, and the placement of where the voids and available space for the fluids to get through allows for where the mineralisation sits. As a result of that shear fabric, it normally forms in veins and lenses of chalcopyrite and pyrrhotite within that mineralised zone. Here's a really good example of where we can see kind of all of the types of mineralised vein structures that we see on site. We have 3 natural cut-off grades that we see from the geology, and it's due to either the density of the S2 controlled copper, and that's normally where we see it in our sort of 0.2 to 0.4 grade zones. When we start to see our sulfide dominant veins and the frequency of them to start to increase, we see that to be in our 0.4 to 0.8 zone, and that's the zone that we largely try to focus on for our stope outlines. And then we see the brecciated sulfide vein stockworks, and this is where they're over 0.8. And these are the 0.8 sulfide ones, are the zones that actually sit within that halo of the epigenetic sulfide veins, and that's why we try to make sure we do our stope boundaries to that, because then we always are getting our high-grade stuff that's contained within. So underpinning all of our stope design work is the geology and how we use that geological information to create our stopes. Our geological domain interpretations are created from our early grade control and resource drilling, and that allows us to define where we believe things will be and then create the domain models that are used for our block models. We'll create a grade control block model based on that drilling information, and from that create our preliminary stope designs. Once the preliminary stope design and outline is created, that's how we design our development and where the development's going to sit for accessing those stopes. Once we're in development, we have the opportunity to collect more geological information, and we look at collecting mapping information and our infrared scans of each face. Our geological data collection that we do during development can kind of be identified in 2 main ways. We have our underground BACS mapping, so our geologists spend a significant amount of time underground every day, and of that they were collecting information. Those maps allow us to identify areas of high mineralisation, but also structural information of it, so helping us identify where in the system we're sitting. It also allows us to get information that is geotechnically useful, of where joints are and how planes are interacting. We also, as mentioned earlier, do a number of spectral scans. So spectral scanning of the face gives us an excellent high resolution image that gives us both geological information and grade distribution information. The image on the right there shows the big blue stope void, which is our Kavanagh 01 stope. And this stope, we will run into some detail on how all of this stoping process has impacted how we designed that over the years. This is all inside of that. You can see all of the spectral scans that we've been taking, and these are all shown as the RGB images. We then review our grade control block model based on that information that we have collected. And we look at the grade control block model and identify, is it matching what we saw? On the level that we have mined, and we've got the development and we've got the mapping, is the high grade zones aligning? Are we seeing them in the correct spot? Is the distribution looking right? Is the structure and how those domain models have worked all correctly identifying the geology before it goes for final engineering stope design? Once we have approved it, then it goes off for drill and blast design. And in our drill and blast design, we try to take into account for a number of other geological issues that for us, because we're a schist-hosted deposit, it means our rock type has a significant fabric to it, which means we do get a significant amount of drill hole deviation. One of the pros and cons to drill hole deviation is that we have to then design for it. Once we learn it and understand how it moves, it means you can use that to your advantage. And you can see in this drill design example here, the outline of the stope versus where the drill holes actually are slightly different. That's because when we've been drilling these holes, we're allowing for the swing and lift that we would see on that side of the drive for the drill, and how the stope we expect to actually fire. that is how it actually fired, and we had been taking a significant amount of measurements of all of our drill holes and of production holes as we were going to understand how the ground moves. And we've been able to feed back that through into this Cavo 1 stope and use it all the way through the design life of it. We also take into account in this one how we're going to fire it and the sequence that we fire it in order to maximise recovery, grade, and boggability, so trying to maximise our free bogging tonnes. Once the drill and blast design has been created, we do a geotechnical review. And this is one of the outputs of our spectral scanning and BAX mapping, is creating these wireframes and planes of where all the jointing sits. So this allows us to have a 3D model of all the joints that we've observed in the development and project them into where they're going to interact with the stope. Once we do that, it allows us to understand best places to put stope brow position, any additional ground support that needs to be used, and therefore tries to give us the best chance of excellent geotechnical performance of the stopes. Once all of those steps have happened, then we pass it off to operations to commence drilling, charging, bogging and hauling of the stope. And the results for us have been that we have managed to create a stope that is over 155 vertical metres. It runs from our 940 level all the way down to the 785. And so that is taller than any of the Adelaide skyscrapers. So it has created a void that is greater than 730,000 tonnes. And when intersected with our 2025 MRE, it comes out at a design grade of 0.9% copper. To date, the panel is actually reconciled at 1.1, and the reason for this variance there is due to those high-grade zones that are small, more discontinuous than our grade control spacing. And by taking it out to that 0.4 to 0.6 kind of cutoff grade, it means that we're always capturing them, so we're always maximising the copper return. The final reconciliation on this stope is to come, as it is still currently in production at the moment, but it has been performing really well. And we've also seen very little overbreak on such a large void, with down to the 860 level on it to date. We had about 4% overbreak, and this has allowed us to do successful extraction of both up and down drill hole panels, including learning about that drill hole deviation and applying that back into the stoping sequence. And it's allowed us to try different things, including the use of long hole risers versus raise bore risers to create the initial stope voids. All of the learnings that we've taken from these stopes, and this stope in particular, we've then been rolling back into all of the subsequent stopes that we have been mining across the deposit. Thank you.